Yo, what is up, guys? Welcome back. I'm not feeling good today. Feeling under the weather, but I thought I'd go in and work a little bit on the OpenGL. I think the last time I streamed was probably about 2 days ago. So we were kind of learning about, I think, shaders or something, but now I've kind of progressed through the episodes of the days. So I think kind of what I'm at right now is let's take a look here. Still learning OpenGL, but I think where I'm at here, let's go to the OpenGL channel series. Still trying to pull it all together, but went through a lot today. So we're gonna be learning about projection matrices and probably model view projection matrices, which is interesting. He kind of touched on a little bit in the math video. So that's kind of the goal for today. We don't have many episodes left, so maybe 10 or so. But the goal is, once we're kind of done with that, just kind of working on probably something 2D at first, and then move into a little bit learning in 3D or something. So yeah, that's the goal. But yeah, let's hang on. Kind of working on probably something 2D at first, and then move into a little bit learning in 3D or something. So yeah, that's the goal. But yeah, let's jump into the problem of the day. We'll start with a Leetcode problem of the day. Take a look here. Set intersection size at least 2. It's a hard problem with a 60% acceptance rate. Give it a 2D integer array intervals where interval. So an interval problem, you give it a 2D integer array intervals where intervals I is equal to start end represents all the integers from start to end inclusively. The containing set is an array nums where each interval from intervals has at least 2 integers in nums. For example, intervals 1, 3, 3, 7, 8, 9, then 1, 2, 3, 4, 7, 8, 9, and 2, 3, 4, 8, 9 are containing sets. Turn the minimum possible size of a containing set. 1, 3, 3, 7. So a containing set is an array of nums where each interval from intervals has at least 2 integers in nums. Then 1, 2, 4, 7, 8, 9, and 2, 3, 4, 8, 9 are containing sets. Turn the minimum possible size of a containing set. Not fully 100% understanding the problem, so let's try and do that. Let's take a look here. 757 set intersection. Set intersection. Size at least 2. For some reason, bro, with me, I don't fully comprehend the problems in Leetcode sometimes. I don't fully understand what they're asking. So that's something I probably need to get better at, but so I like a better explanation. One set of integers, S, you choose the numbers such that every interval has at least 2 numbers from your set inside of it. For each interval LR, it must contain greater than or equal to 2 distinct integers from your chosen set S. Find the smallest size of S. Just in size. 1, 3, you must pick for interval 1, 3, S must include at least 2 numbers from 1 and 3. Valid to choose 2 and 3. For interval 3, 7, S must include at least 2 numbers from 3 and 7. 3 and 7 is fine, 4 and 5 is fine, etc. For interval 6, 9, S must include at least 2 numbers in S9. Pick numbers so that all intervals are happy while picking as few numbers as possible. Okay. So we'll give them 1, 3, right? So a containing set is an array where each interval from intervals has at least 2 integers and nums. Turn the minimum possible size of a containing set. So in this case here, we picked 1, 2. In this case here, we picked 4 and 7. In this case here, we picked 8 and 9. So here we picked 2, 3. Right? Then we picked 4, 8. No, we picked 2, 3. We picked 3, 4 again. Then we picked 8 and 9. How's it going, dude? What's up, Crosshair Hero? It's going good, man. Not feeling the best today, but it's going. So, trying to think here. So if I'm thinking about this problem correctly, let's jump over here. Let's move this to the side. If I'm thinking about this problem correctly, we're given these intervals, right? Okay. Oh. Sometimes I don't think about these problems correctly, but we're given these intervals, right? We can pick any 2 numbers from the intervals. I think that's what I'm getting at. I want to clarify that. 2 numbers from the intervals. For each interval, I should pick 2 numbers. View ways for correct observation. You must pick one global set S, such that for every interval, the count of numbers from S that fall inside that interval is greater than or equal to 2. But you might use the same numbers for many intervals, meaning some intervals may get 2 numbers, some may get 3 or 4 or more because they overlap with others. Some may share numbers. Okay, so you're not always picking 2. I have a feeling that this is a greedy problem in some way. I don't exactly know. Long streak of easy questions. Yeah, I'm having issues too. You nailed it. Need to return the minimum size array that has minimum 2 values from every interval's I. Create a nubs array from scratch. Yeah, I have a feeling this is gonna be some sort of greedy problem. I'm gonna play some music, low key, but so we can pick. Okay, so let me clarify here. So we have to pick at least 2 numbers. So we have to pick at least 2 numbers. We don't pick 2 numbers per interval, we pick numbers for one global set S. Each interval must contain at least 2 numbers from that one set. This is the misunderstanding. You're thinking from pick 8 numbers, pick 10 numbers. This is not what we do. That's wrong. We want the minimum. Okay. You build one shared set of numbers S and all the intervals reuse it. Example, 2, 5, 2, 6, 4, 9. So let's pick 4, 5. Check each interval. Contains 4, 5. Okay, it has 2 numbers. Contains 4, 5. Okay, it has 2 numbers. Contains 4, 5. Okay, it has 2 numbers. We only need 2 numbers total for all intervals, because those 2 numbers lie inside every interval. This is the goal. Maximize sharing, minimize new picks, cover every interval. Well, you must satisfy for each LR count how many numbers from S lie between L and R. Let the count be K. K is greater than 10. Okay. Followed your LinkedIn and GitHub from last stream. Gonna try and keep up with your progress on there. Thanks, bro. Appreciate that, Crosshair. I'm gonna build a. I'm not sure what I'm gonna build yet. Kind of after learning OpenGL on Channel Series, I'm not 100% sure exactly what I'm gonna build yet, but it's gonna be something. Maybe we might just get started with a Minecraft clone and kind of just work our way from it. That's the ultimate goal in OpenGL. I want to build something like Minecraft. I feel like every dev like kind of goes through that, so kind of want to build something like that, but you know, maybe I'll think of a better idea. I don't want to jump too quickly. You know, I've done something 2D before, not using OpenGL but something else, but using SDL3, but you know, kind of I do want to experiment in 3D, even though it's a lot harder. I've never done anything in 3D, but you know, again, it's all part of the learning process. So let's see here, right? Maybe I'm thinking here, right? We can keep some sort of set, right? Our set allows us to check every single input, you know, in all one time, right? So I'm thinking we keep track using a set, right? That's my first kind of thought, right? We can keep track of an unordered set of integers, right? And we can call this like hashy or something, right? Appreciate you sticking around, Crosshair Hero. Appreciate I do like to stream every day, but sometimes it's hard with like class at night and stuff like that, so it's kind of AIDS, but you know, it is what it is. Right, so we can use a set here, right? This is what we're going to use to like keep track of our length, right? You're given a 2D array integer represents all the integers from start to end inclusively. A containing set is an array nums where each interval from intervals has at least 2 integers in nums. Okay. Also, I have been inspired to start working on personal projects as well, so thanks for that. Appreciate that, dude. I mean, that's kind of the goal too. It's pretty nice hearing stuff like that, so I really appreciate that. You know, inspiring other people too. So there's a little bit of human, there's a little bit of a human in the audio. Oh, okay, I think you're talking about me. Okay, appreciate that, but yeah, you know, it's nice inspiring other people. I've had that. A couple people tell me that it's kind of nice, so appreciate everyone that kind of joins in and, you know, just listens or rides along with me. So but yeah, let's see here. First of all, probably what we want to do here is we probably want to loop through. Let's loop through this array here, right? So let's kind of do a normal loop, right? Because we might have to access the indices here. I don't really know, but let's go intervals dot size I++, right? We probably want to grab the values, right? So for const auto reference. Sorry, I mean hum noise, like a constant bass hum. It's probably my mic, dude. Hang on, let me fix it 1 second. Sorry, yeah, I got a shitty ass mic. Well, so it's not shitty, but it's old. Is that better, or I hope that fixes it. I don't know. Is it okay? That got it. Okay, sweet. Appreciate it. Cool. Okay. So we know we have 2 values every single time, right? So there is structure binding here. So for const auto reference, pair in, I guess, I, right? Let's just see out you know, pair dot, I think it's pair dot first. NL, oops. NL, cout, pair dot second. NL. Let's just make sure that this, what are we returning here? Returning an integer here, so let's just return something like 0 for now. Console reference pair invalid expression of type int, no viable begin function. Can't remember what the syntax is here. I have to look this up. I think I'm missing some square brackets here or something. I think it's, yeah, console reference. Whoops. I think you need LR in I. Use L and R directly. Okay. So then we would just print L, right? Alright, print R. Let's see what that gives us. It's getting another error here. Invalid range expression of type int. Console reference LR in I. Guess we can also do const auto reference interval. And then what? I think it's like interval dot first, right, or something. Interval dot second. Sometimes I can't remember the syntax, but nope. I'm still getting something wrong here. I don't know what is. What is this syntax issue? I is just an index, not the vector. So we don't use I. Whoops. Oh, whoops. Would it be intervals I? Is that what I'm missing? Yeah, right, because that's the index. Intervals I. Is that? Interval. I remember reference base. In const is not a structure of union. Okay, let's just go back to the structure binding version. Const auto reference LR in intervals. Maybe this is what it is, and then we can just go LR here. LR. Just kind of want to set this up. Nope. Console reference LR in intervals. Would this be like intervals I? Dude, I don't know what the syntax is. Nope. What the fuck? What is this syntax, dude? What am I missing here? Cannot expose on class 3 in const. What, we get rid of the const? Bro, what is going on here? What is this? Really, bro? Maybe we could just loop over. Oh my phone. Oops. Let's do. Maybe we don't even need this loop. Let's get rid of this. Let's just do 4. Yeah, would we even need this loop? Vector. Oh yeah. What am I doing? Yeah, shit. Okay, so const auto reference L R in intervals. I think this is what my issue was. C L and L. C L R and L. Oh my gosh, dude. I have no idea what is wrong here, dude. Cannot decompose. I don't even know what this error means. What does this mean? I thought it would always be 2 values. Wouldn't this work if it's always 2 values? No. Maybe not able to do this because it's in the vector const auto interval in intervals. Const auto reference. Then we can go interval dot first. Interval dot second. Okay, so 0. Go back to old school. Finally, dude. Okay. All right. So now we're accessing every value. 1, 3, 3, 7, 8, 9. Jeez, that took a lot longer than I wanted it to. But let's take these strange. So intervals I dot length is always going to be 2. Intervals dot length is greater than 3,000, right? So what do we want to do? We want to grab the interval, right? And then we want to... This shit has me tweaking. Had reference. Yeah, I do my references over there. I think it's easier like to think like const auto reference and then the variable name. I don't know. It's just me, but... I guess it's just personal style. Did you solve this one, Becca? This problem? I'm still not fully sure if we only have to pick 2 numbers. Continue sentence. So we grab our intervals here in this case, right? And we just pick 2 numbers from here, right? So 1, 3. They pick 2, 3. In here they pick 2, 3. In here they pick 2, 3. Right? In here they pick 3, 4. That's why they get 3, 4. It can be shown that there cannot be any containing array of size 2. Okay. So let's do this. Let's do... so we have our hashy. That's going to hold our numbers, right? We have our 2 intervals, right? We want to check if every number in those intervals is inside of our set, right? So maybe we can hold every value that's not inside of that. But the thing is, time complexity grows from there. I couldn't solve it solo, to be honest. I had to get help. Okay. Hear me out. This is my thought, right? Hear me out. Becca, right? So, I'm thinking we use a set here, right? And my reasoning to use a set is because, obviously, it's O of 1 access time, right? Here I loop through the intervals, right? I grab, you know, our left and our right, okay? And I loop through our left and our right, and I check if it's inside of our set, right? And I keep a count of what is inside of the set. Because I keep a special count, right? We need at least 2 values, right? So if I have already 2 values in the set, then we can skip it from there. If not, if we have 1 value, then we can just add 1 value from our missing interval. I mean, from not our missing interval, from the current interval we're looking at, right? Is that a good approach? I don't know. I mean, I don't think that maybe it's too slow. I don't know, but I mean, I guess you might as well try, right? Let's think about it here, right? So let's see here, right? How do we want to do this? Can we return 2 values from a function in C++? I think you can. Is it like SCD variant or something? Or SCD tuple provides a generalized solution. Can you return a vector and a int from a function in C++? So I'm back. I had to pick up my kid from school. Dude, you're chilling, bro. Use a struct. Function can return an SC vector and an input encapsulating them. Okay. Let's think about this, right? SCD pair. Hold 2 homogeneous values, tuple. We could use a pair, we could use a struct. I just don't know if this is like the right way to go about it, to be honest. Use the length of this to return. I just don't know. What I don't know is that I don't know the way that we should be adding the values, right? Like, we can pick 2 values to add from this, but what 2 values can you pick? Like, we can't guarantee the 2 values that we're going to pick from this pair, right? Add the minimum needed. Sort intervals. Right, inside of LI, use 2 pointers. Yeah, I'm not sure, to be honest. Are you going to use a set and grab values that are not in the set from each interval? I mean, yeah, that was my first choice, but obviously I don't think that'll work, right? Because I can't guarantee myself which value to pick. So maybe I don't know. I don't really know kind of how to think about it. The constraints is 0 to start to end. And we'll start like 3,000. Ordered in sorting order. We always add the far right value. I don't know any C++. My degree was more on Java and JavaScript than anything. Ah, man, it's totally okay. I don't think that will work. If we have 1, 3, 3, 4, what if you grab 1 and 4 and then 1 is not enabled 3, 4? Yeah, that's literally what I was saying. Like we can't guarantee the number that we're gonna pick, right? That's why I think like a greedy, like it is a greedy problem because you gotta. I just don't know how to pick them. I don't know how to guarantee like what to pick, right? Maybe we always pick the far right value, right? With a far right value, maybe that can guarantee an overlap, or have our guarantee to at least overlap. These are already in ascending order, huh? You know, like maybe like, you know, we have our intervals here. Greedy, right? We have our intervals here. You know, what if we always pick the far right most value, right? So let's think about this here, right? Let's say we look at intervals 1, 3, right? Our set has, you know, whatever values that we want, right? In this case here, we always pick the far right most values, right? So we would, in this case here, we'd pick 2, 3, right? We move on to this example here, right? We see that we have 3, right? Then the far most value we want to pick is 7, right? So we would obviously pick 7, right? That's the far right most value we can pick. Then we go here to 8, right? Well, 8, 9 doesn't exist, right? So we would just go like 8, 9, right? So in this case here, we'd return 5. So we would get the correct answer, right? What if we picked... Okay, what if we have our intervals here, right? We have 1, 3. Let's grab this here. Right. This is our other test case here. What if we picked... Okay. In this case here, we look at our first interval here. We pick the 2 far most right values, right? So we have 2, 3 inside of our set, right? Here, we notice we have 2, 3 already here, so we don't have to do anything, right? We skip this value. We're at 2, 5. We have 2, 3 already. Doesn't have to do anything, right? In this case here, we have 3, right? But we pick the far right value, which is 5, right? In this case, that thing would be 3. So this would work here, right? The thing is, they don't give very many test cases, so this maybe doesn't work. I don't know. Okay, so then we're given this array here, right? Let's see. Okay, so we're given 1, 2, right? So we'll start our set off with 1, 2, right? Then we check 2, 3, right? We see we have 2. We add the far most right value, right? So we would just add 3. In this case here, we have at least 2 values, right? We have 2, 3, so that's fine. We skip this. 4, 5, right? We don't even have 4, 5. So therefore, we have to add these values, right? So in this case here, our output is 5. But the thing is, I don't know if that guarantees us every single time. Like, we only have 3 test cases, so I don't know if this works technically. I don't know. I don't know if that's the right thinking. try that. You can work from there. Okay. Alright, I guess we'll try. I mean, why not? Okay, so we look through every single interval, right? We have our hashi, right? What's the best way to do this? For int, let's do left is equal to interval 0, right is equal to interval 1, print, right, for int left int is equal to left, L is less than right, L plus plus. Okay, so how do we want to go about doing this? Well, there's no way this solution is going to work, I don't think, but I mean, we'll try it anyway. How can we pick the far rightmost value, right? So hang on, 2, 3. How can we guarantee the far rightmost value every single time? Well, we have to loop from the back. We have to keep some sort of data structure to documentation. Set. Find elements for the specific key. Always going to return what? Return number of values of the key. 1 or 0. Okay. Maybe we don't really need to loop, right? We can just do, well, like, if s.count r, right? We can keep some sort of count here, right? In count is 0. If s.count r, we can increment the count. If s.count r minus 1, we can increment the count. If count is equal to 2, then, well, we don't do anything, right? We would just continue, right? If count is equal to 1, then, right, we do something, right? Otherwise, if the count is 0, then we're at least going to add we add both, right? So we do Hashi.add r, right? Hashi.add r minus 1. Is it add, bro? Or is it insert? I think it's insert, low-key. Insert. Yeah. Hashi.insert r. Hashi.insert. Count is equal to 1, right? We do if s.count r, then so if count is valid, we hashi.insert r minus 1, right? Because that's the element we'd want to add. I guess else, right? If it's false, it has to be the other one, right? Hashi.insert r. Bunch of fucking if statements, bro. Okay. You just return the length of this, right? What is the fucking length of this? Dot size. Return. Hashi.size. This is literally a bunch of if statements, bro. Fuck me, bro. Left is equal to equal. Whoops. We need this to be an integer. Integer. S.count. I'm going to declare identifier. S.count. Oh, whoops. It's hashi. Whoops, not S. Hashi. 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 Yep, hashi. Okay. This should be good. Count R. What do we have? Oh, whoops. We had right instead. Whoops. Thought we were inside of our for loop that we declared earlier. Right. 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 Take the left and the right. Hashi.count right, we count. Hashi.count. If count is 2, we continue. We don't need to do anything. If count is 1, we check. If hashi.count right, then we insert right minus 1. Right? Otherwise, we insert what we're at. I think that's correct. If count is 0, we add both. What am I missing here? Maybe this won't work. I mean, that's what I thought. Let's figure out. Let's kind of run through this test case here, right? So 1, 3, right? We would add 2, 3 in this case, right? In this case here, you see that 3 exists, right? So, oh, okay. Right, if I think that's where we fucked up here, right? Because if hashi.count right, we're inserting right minus 1. Wait, no, that should work actually. If hashi.count right. See, I don't think just checking these last 2 values would work. Wouldn't we have to check everything? I think I'm getting this wrong. I might have to watch a video, bro. I'm not sure kind of how to go about doing this. You have to sort it if you're using greedy. Okay. Sort of which way though? I thought... See, I thought in this case this was already sorted in the case that I wanted, right? In ascending order. But it's failing on these test cases. Yeah, I don't know. Let's take a look at... Let's take a look at his video. Let's see if he has one.
AT&T's been carrying America's calls since 1876. When you've been around that long, you can spot a hustle coming.
Another day, another dollar from making these videos. At this point, I think I'd be better off getting a job at McDonald's or something. But anyways, today let's solve the problem set intersection size at least 2. So we're given a 2-dimensional array of intervals. And as soon as you see that, I mean, when you see an interval problem, the name of the game is almost always going to be sorting. And this problem is no exception. Typically, we can do some kind of sorting and then greedy based approach with this.
Okay, so at least I had the right idea. I mean, I kind of realized that.
Or with all interval problems. If you don't know that yet, it's probably because you have not gone through the Leetcode 150 or the 250 list, and specifically the intervals section. So I would recommend doing that if you haven't. But I had a bit of trouble even understanding what this question was asking, to be honest, so I'll try to make that clear. In this example here, we're given some intervals. So just to draw it really quickly, we have 1, 3. That's going to be like this. We have 3, 7.
The only reason I knew this shit was because I did Leetcode intervals a couple days ago. Okay. Yeah, I've done Leetcode intervals too a couple days ago, but honestly, not a couple days ago, sorry. Probably a year and a bit ago, but
that's going to be like
it goes out the window.
And lastly, we have 8, 9. It's going to be over here. And so none of the intervals are really overlapping much. I mean, these are overlapping, and we do include the endpoints, so keep that in mind. And also, I think they guarantee us that all of the endpoints are going to be between 0 and some positive number. And also that each interval, we're never going to have like a single point interval. The 2 endpoints do have to be different. The second one is always going to be greater than the first one. So knowing that, you can kind of read through the description where it says, the definition of a containing set is an array of numbers such as this one or this one, where each interval from the list has at least 2 integers in that list of numbers. So the reason that was confusing to me is when they said has at least 2 integers, I took that to mean like the endpoints, but that's not what they're talking about. They meant that like this interval is defined as 1, 2, and 3. So at least 2 of those points have to be in the list. Same thing with this one. It's defined as 3, 4, 5, 6, 7. At least 2 of these points have to be in the list. And then same thing with this guy. So they give us 2 that are possible. They give us this 1, 2, 4, 7, 8, 9. That's 1. And that has 6 points in it. And they give us a different one over here. 2, 3, 4, 8, 9. So the reason we prefer this one is it only took us 5 points. So what we're trying to do is create the minimum possible containing set, and we actually don't even have to create it. We just need to know the size of it. But I think in this problem, we could have done either one. It's just as easy to create the set as it is to figure out the length of it. So now we kind of have an idea, and this is why I said sorting is the name of the game, because obviously if there's some overlap, we want to definitely pick the overlapping sections as like the points so that we can kill 2 birds with 1 stone. So naively, you might try just sorting them in ascending order. So using the first point to sort them in ascending order. And if there's a tie, maybe we have this interval over here. So these two both start at the same position, but they end at different positions. Maybe we'd still do this in ascending order. So this interval would go first because its ending point is smaller than the other one. We're basically using the end point as the tiebreaker. So that's what you might naively try. And so let's say we did try that, and I'm going to use a more interesting example than this one, because in this example, it actually does work out pretty nicely. So I guess I will just quickly go through this example. Imagine we're iterating over these from left to right. We see this interval. Okay, we don't know much And assuming we took care of everything that came before it, what we would want to do at this point, and since it's the first interval, we have to pick 2 points in this interval, but which 2 points would we pick? Would we pick like the first 2 or would we pick like the last 2? Those are our only choices in this case. Well, my claim is definitely going to pick the last 2.
Okay, that's what we thought. So that's a W. That's a W.
Because that maximizes our chances of overlapping with the next interval, given that the next interval is definitely going to start after this one. Now, we have no idea where it's going to end, but we definitely know it's going to start before that. So that's what we would do. We'd pick these 2, and then we would go to the next interval. And we'd keep these like in 2 variables, let's say, and our variables are going to be 2 and 3. So now we're here. This interval starts at 3, it ends at 7. What we would check is, do both of these intervals fall in this one? Well, no, they don't. Like, we're trying to be greedy. We want both of them to fall in here. Then we don't have to add any new points to our containing set. But this time they don't. Okay, then we would check, well, at least does the last one start in here? Is it contained here? Yes, it is. So we got 1 out of 2. And then for this one, well, we would get rid of it. Now we'd find a new point in this one, and we'd probably pick the last one to maximize our chances. So it seems like it works, but let me show you a really simple counterexample to this. And let's say this interval was bigger like that. And let's say then we have another interval that does start after this one, but it actually ends before. Let me actually make it really small. Let's just make it 2, 3. Then I don't know what else I'll add here, but maybe I'll change the rest of this example later. But just from this one, we reach an issue because we're going to go through this one first, this one second, and this one third, because we sorted them based on the starting time. So we pick this one. We want to pick the last 2 to maximize our chances because we know for sure all the future intervals are going to start after this one. But we don't know that they're going to start after this one ends. So that's the edge case. So that's the problem here. If we pick these 2, we actually didn't maximize our chances. We kind of ruined our chances because had we started with this interval, we could have picked these 2, and then we would have guaranteed that the next one does end before this one. Maybe it doesn't start before this one ends, but still. So the point I'm trying to make is if we're trying to be greedy in the way that I talked about, trying to pick the last points possible to maximize our chances, we shouldn't sort based on the starting time of these intervals. We should actually sort based on the ending time of these intervals. Okay, so far so good. We can try that. And in this example, it will work. Like I'm going to get these 2 points as my first points chosen. So that's 2 and 3. And then I'm going to go to this next interval. I'm going to find that these points are already contained in this guy. So that's good. And then I'm going to go to this interval. And then we're going to be forced to pick 2 new points. So that'll have been 4 points total. And that works for this example. But once again, let me show you a counter example. Well, it's not really a counter example, but it kind of helps us arrive at a more precise solution. So what I'm about to explain to you next is probably the most complicated part of the problem. It's really, really subtle, so it's easy to miss this unless we really go through the example and dry run through it. So I'm going to add another interval. Let's make it 4, 5. And so I'm picking this interval because it also ends at this position. So we already said we're sorting based on the end value, let's say the right part.
I suck at Leetcode, honestly, dude. Yeah, I mean, I'm not that amazing
Part
either,
of the
I'm
interval,
pretty
and we're doing that in ascending order. But if there's a tiebreaker, what do we do? Do we then just sort based on the left value in ascending order? Or do we sort based on the left value in descending order? And at first, it might seem like it doesn't really matter. And that's because it doesn't. You can code it up both ways, but I'm going to show you why doing it in descending order based on the first value is a lot more simple. And I'm going to use some variables now. Now we're actually going to go through the dry run. Just a few variables. One is going to keep track of the result, and that's going to be an integer, but just to make it really, really clear, I'm actually going to make it an array so you actually know exactly which points we picked. So let's do that. And I'm also going to keep track of my last 2 points that I have picked that are a part of the solution set. So I'm going to call them P1 and P2. P1 is going to be the previous one, and then P2 is going to be like the most recent one. So if we had 2 points like this is P1, this is P2, just to make that really, really clear. So now let's start. And we're going through this from left to right using the ending values in ascending order. And I'm going to initially try to do it in the other way. I'm going to try to now also do the left values in ascending order as well. So we're going to first go through this guy, and we're going to pick the last 2 points that this is a part of, because we're trying to be greedy. We hope that the last 2 points of this are also a part of the next interval, which is going to end before this one, or rather end after this one. So we pick these two. We're going to get 2 and 3 here, and then that's exactly what these are going to be as well. In that case, we would have just incremented this by 2, by the way. And we would have known that because P1 and P2, let's say initially they start at -1, because those are definitely going to be out of bounds. And then what we're going to check is just that P2, which is -1, is less than the starting of this one. And we know that P1 is always going to be less than P2. So if that's the case, then we know that neither of these belong to this interval. So we have to pick 2 new points. So that was the initial case. Now we're here. Now we're going to go to this interval next. And we're going to check, is P2 less than the beginning of this? Is it less than the left? Is it less than 1? No, it's not. So that automatically tells us P2 is definitely a part of this interval, because we know that P2 was a part of the previous interval, and this one definitely ends after that one, or it ends at the same value. So we don't even have to check that P2 is less than this guy. And so since we found out that P2 is bigger than the left, we already know it's less than the right. That means it falls somewhere in here. So that's how I'm going to code it, at least. So now we know P2 is in there. Let's check P1. Okay, is P1 also greater than the left? Because we know P2 is somewhere in here. P2 is over here. P1 is definitely less than P2. So if it's greater than the left point, then we know that P1 also falls somewhere in here. And so right now it does. So that tells us both of these guys are in this interval. We don't have to do anything. Keep them the same. Okay? And next, we're going to get to this interval, and we're going to find that P2 is actually less than the left here, which is 4. So neither of these guys falls in this interval. So then we have to pick 2 brand new ones. We pick the last 2 points of this. We pick right and right minus 1, which is going to be 4. So we'll replace both of these with 4 and 5, and we'll add that to the result. So this one actually worked out in this example. And had we done it the other order, had we done this one first and this one second?
Okay, bro, I'm starting to get fucking confused, dude. He's talking way too fast. Maybe if I read his code, let's see what he does. Left to right. So he sorts based off the first value, and then the second value. P1, P2, they must be the previous points, right? So left, right in intervals. If P2 is less than left, we add 2. P1 is equal to right minus 1. P2 is equal to right. Also, if P1 is less than left, whereas plus or equal to 1, if P2 is equal to right. He hasn't typed that part yet.
Okay, you can see that -1, I believe.
Bro, look at Python, man. It's so easy. Yeah, I know. It's easy to look at. I'm honestly not sure about the way this sorts, though. Okay, so using a lambda here to sort. There's C++ sorting fucking confuses me, dude. Like intervals.begin, intervals.end. I can't remember, dude. Find the state of the lambda, return type, body, parameter list. return type. Value descending and tiebreaker on first in descending. How do we do this? So we sort intervals dot begin, intervals dot end. We sort based on, I believe this is the return type. Const vector int reference a const vector int reference b. If A1 does not equal B1, turn A1 is less than B1. This should be ascending, sorry. So if I always get confused with C++ fucking sorting stuff. The lambda is kind of what fucking confuses me the most. Slam takes A one interval, B another interval. You would decide whether A should come before B. Okay, so if the values are different, right? So if A1 does not equal B1, then we return A1 is less than B1, right? Ascending, right? Otherwise, we would just return based off descending order, right? So it would be what, B1 is less than A1, I think. I'm not sure. Sorry, A0 is greater than B0. Okay. So we would return A0 is greater than B0. Shit's fucking confusing, bro. Like, descending. Let's vector A and B. Oh, bro, I just need to get my C++ better, man. It's tough. So I think this sorts, right? Can't sort of reference interval, in intervals, left, right, print, in count. Const vector int reference b. Oh, there's a dot here. Why the fuck is there a dot there? Type void does not provide a subscript operator. I think go like this, and then we would close this off here, right? No, maybe we close this, close that, colon. I think this is what it is. Yeah, okay. We get 4 here, we get 6 there. For const auto reference interval in intervals, int left, int right. Count 0, hashy.count right, count plus plus. If hashy.count, count plus right, count plus plus. If count is equal to 2. If it does have the far right value, we add value before that. I mean, we're gonna fail on some test case here in this, so. Man, I wish I could solve this problem on the spot. I'm gonna turn down the air conditioning, bro. It's hot as hell in here. Oh, dude, it's so hot in my room right now. It's crazy, bro. Okay, let's look at his code now. So we're doing the same thing as him, right? So he goes, let's create these values first, right? He starts off with previous values, right? So int p1 is equal to -1, int p2 is equal to -1, right? For const auto reference interval in intervals, we'll grab our left and right. We have our count, right? I think obviously mine here is wrong here, so let's get rid of this. What does he do here, right? So he goes, well, if P2 is less than left, right? Res plus or equal to 2. P1 is equal to right minus 1, and P2 is equal to right. So let's do that, right? If what did he do? If P2 is less than left, if P2 is less than left, then P1 is equal to what? Right minus 1. P2 is equal to right. Yeah. Res plus or equal to 2. Right, so we need some sort of res. Let's create some res value. Int res is equal to 0. Let's res plus or equal to 2. Right, let's just push back these values, right? So res dot pushback P1, right? Res dot pushback. Just so we can see kind of what we're pushing in here for debugging purposes, right? Okay. Then he goes, well, else if that's not true, what would happen if that's not true? Think in your head right now. So if our previous value, so this is where we're looking at an interval that is in between, right? So if P2 is less than left, we would do that, right? If P1 is less than left, then we can guarantee that there's at least one value in there, right? I don't like the way he's doing it. Trying to think, dude. If P1 is greater than or equal to equal to left, and P1 is greater than or equal to left, and P2 less than or equal to right, maybe P1. Go and play some Battlefield. Have a good study session. See you later, bro. I appreciate you stopping by, man. P1 is greater than or equal to left, and P1 is less than or equal to right. Then what? Count plus plus. If fuck me, dude. Bro, I can't visualize this in my head, bro. P2 is greater than or equal to left, and P2 is less than or equal to right. Then we can count. If count is equal to 2, we just continue. If count, I don't know if this is correct though, but P1 is greater than or equal to left, and P1 is less than or equal to right. Let's think about this, dude. Fuck me, dude. This shit's so fucking... So our P1 is -1 right now. We're looking at this value, right? So in this case here, we're going to add both values, right? So our thing is going to be 1, 3, right? And then we're going to set our previous value to be 2, 3, right? That's what it's going to be now. So then we're looking at this here, right? Our previous value was 2. So if we have 2 here, P1 is greater than or equal to left. Yeah, bro, I'm stuck. I don't know. I'm fucking stuck, bro. I can't solve this problem. There's no way I can do it, bro. I don't know. I'm gonna give up. It's been too long. It's fucking driving me insane, bro. I'm like fucking sweating bullets right now, dude. Yeah, Becca, bro, I can't do it, dude. I can't wrap my head around it, dude. I'm literally driving myself insane right now. This one is really hard to grasp. Yeah, bro, it's literally insane. As much as you see it. I have to rise it. Oh my gosh, dude. It's tough, bro. Okay, so I think, so this is correct. So the way I was thinking about it is correct, right? If we're inbounds, we increment our count. If we're inbounds, we increment our count. If our count is 2, we continue, right? If our count is 1, we do something else, right? If our count is 0, right? Then we do something else. What's up, Skrix? Good to see you, bro. If our count is 1, this is what I'm missing here. If our count is 1, at farthest right possible in none 1. So insert new none. This problem's pissed me off, dude. I'm just experimenting with VMs. What are you up to? Well, as you know, I always start off the stream with a LeetCode problem. I'm getting absolutely cooked on this problem. I've probably been spent about an hour and a half on this problem, which is fucking ridiculous. I'm still trying to fully understand it. And then I plan to do some OpenGL. Probably about an episode or two of Chono's series. Probably, I've been working on it throughout the week. So we got about, I think, less than 10 episodes. Maybe about 10. I don't know. But I kind of want to finish it up soon so I can, you know, kind of start thinking about building my own projects and stuff like that. So, likely to fail. So what is the end of that? Bro, there is no way I would have ever been able to solve this problem in an interview. No chance, bro. Like, there's no chance, bro. Crazy. Unless, obviously, maybe if I've seen it before, maybe, but, like, probably not. Like, give it a couple months, this shit goes out the window. Like, so, to be honest, I don't know how to write this part, but apparently what we have to do here is go int new num is equal to right. Grab the rightmost value. We insert that. So stop pushback. Right. Pushback. New num. Right. P1 is equal to P2. P2 is equal to new num. So our far right val. I just don't get why we're making P1 equal to P2. Old second largest becomes first. And then our P2 is our far right value. Because we're adding one value, right? But if we add 2, then we must... our int first is equal to right minus 1, right? Our second is right. Yeah. We insert that, so s dot pushback. S dot pushback, right? Second. We then update P1 to be equal to first, P2 to be equal to first. Sorry, second. Oops. Then we just return dot size. So that's what I was missing. This part here, it was confusing. Think about it. I think I'm understanding it, but it's like still fucking all over the place. I'm also not feeling good, so. But I think I would have got cooked on the problem either way, so. Let's see if this returns. I probably made some sort of error or something. S dot pushback. What do we make this? We made this. I guess we're thinking about a vector here. Maybe we can just use a hashy, bro. Probably easier just to stick with the hashy instead of using pushback. Kind of all over the place, but it's whatever. This solution looks so easy to think about, dude, but there we go. Okay, so we got it right. I mean, bro, that problem was fucking tough, man. Like, there is no way I would have been able to solve that in an interview. I don't think I would be able to resolve this again. Just writing this alone was like, well, I mean, I got help writing it, so I didn't really write it alone. But, you know, lambdas fucking confuse me in C++ still, so it's like, fuck. Need to get better with it, to be honest, but I don't know. I don't really write a lot of lambdas, so... Lol, same. Yeah, dude. Bruh, dude. So AIDS, dude. Fuck. Some of these problems today, bro, make me so sad sometimes, bro. Like, man. Dude. Need like a soundboard or something, bro. Like, click some buttons and shit on the soundboard, dude. Makes me sad, bro. Makes me feel like I'm stupid, you know. Even though I'm not, I don't think I am stupid, but like, you know, sometimes it gets me down, you know. But it is what it is. Maybe we can do some of that cheers me up, bro, because we just got cooked on that problem, dude. Fuck it, dude. We'll just go to OpenGL, man. Fuck Leetcode, honestly. Like, do it to warm up, bro. And we do some interesting stuff, you know. Let's take a look at this.
My name is Eternal and welcome back to my OpenGL series. So last time we talked about maths and we started getting into maths and all the math-like topics that will come in the future in this OpenGL series and in your graphics programming journey. Today we're going to be specifically focusing on one small part of that, which is projection.
If this comes up in an interview, I'll just introduce myself and leave it there. Yeah, bro. It's tough, man. It's tough.
Projection is one of the biggest actual things that we need to solve when it comes to rendering graphics on the screen. It's part of the...
So a little bit of a background. I know, like, the last time I was on here, I think we were, like, doing something down here. So I've watched about 5 episodes from then. I did a little bit of, like, his maths video. I mean, I call it math, but his math video was kind of introduced a little bit of, like, projection matrices. And I'm still kind of struggling to, like, grasp it properly. So hopefully this video maybe clears it up a little bit. I know I got to like write my own code and like, you know, do my own project to like fully, that's how me personally, that's how I learn. But, you know, I think it's always a good introduction just to like kind of follow a tutorial to kind of learn the basics and stuff, or else like, I mean, it's very hard to learn. So I don't know. I'm still kind of all over the place. This is all still very new to me, this graphics programming. So hopefully, you know, as I keep progressing, you know, it's, you know, exciting to like look back on these streams and kind of see where I came from. So I don't know. But yeah, just a little bit of
the transformation pipeline, which we will continue to explore over the coming weeks. But today I just want to focus on projection, and this is not going to be a super long episode because I don't want to overcomplicate this for you and have you scratching your head. We're not going to talk too much about the technical details and how the maths works, because that is completely irrelevant for 99% of cases. I know they're probably...
Thing is, bro, Chono is Australian, right? And I'm Australian too, but I have never heard someone in Australia my whole time growing up there. I have never met someone that calls it maths. I don't know. It's kind of odd to me, but maybe that's like, I don't know. Maybe Australia's a bit more like Americanized, maybe. I don't know. But because I looked it up, I was like, maths and math, like what the fuck is going on here? Like, but apparently maths is for like, you know, British, you know, British countries, British colonies, whatever. But math is like more like Americanized, you know, American Canada. I don't know, but who knows? So
a bunch of you interested in how it actually works so that you can kind of write your own version of OpenGL from scratch or something. Well, we might cover that in the future. But today, practically speaking, what is projection in OpenGL? How does it work? And why do we use it? So to put it simply, projection is just how we go from having some kind of arbitrary coordinate system in our 3D world, or 2D world, doesn't matter. I mean, 2D worlds are really 3D anyway as far as OpenGL is concerned. It's how we go from having coordinates or vertex positions in that space to being able to somehow map them to our window where we're actually rendering on our computer screen. So we have to project them somehow onto this 2D surface. You might have this massive 3D world with hills and terrain and characters and all of that, which in the end obviously just boils down to a bunch of triangles which are made up of vertex positions, but in the end that 3D world has to somehow be rendered onto our 2D monitor and into our window. That is what projection is. It is essentially the maths that converts all of those 3D points in space into something that is in a 2D kind of window. That is what projection is. So forget everything you know about projection or whatever, that's all it is. It is as simple as that. Now, projection will now be rendered onto our 2D monitor and into our window. That is what projection is. It is essentially the maths that converts all of those 3D points in space into something that is in a 2D kind of window. That is what projection is. So forget everything you know about projection or whatever, that's all it is. It is as simple as that. Now, what do I mean by convert into positions? What does that even mean? The actual transformation that happens with a projection matrix, which we kind of talked about last time in the maths video and we will touch on today as well, is we just convert all of those positions that we have into something called normalized device coordinates, which is basically some kind of normalized space that we can then map to our window. Now, a normalized space means that literally a coordinate system between -1 and 1 in every axis, X, Y, and Z, right? So what I'm saying is that picture that you have a window, resolution does not matter at this rate, doesn't matter what size your window is. All that we know is that the left side of our window, let's just say we're rendering full screen, so the left side will be -1, the right side will be +1, the bottom will be -1, and the top will be +1. Let's not worry too much about Z at this point because that's not as...
Z, bro, let's go, man. You hear that, bro? Z. That's the way to say it.
Important to visualize as X and Y. So that's it. We have our computer monitor, we have our window open where we're actually rendering all of our graphics, and that is between -1 and 1. That is how that is the space that we need to have all of our vertex positions in so that we can actually start rasterizing stuff onto the screen. However, what we have is like this 3D world or maybe this 2D object somewhere on our screen, and we need to convert it into that space. That's what a projection matrix does. And in fact, up until really last episode, we have not been...
I'm gonna grab some meds really quick. I'm not feeling good, so... I'm gonna grab some meds. I'll be back in a second. 1 second.
Using a projection matrix, which is why you probably heard me say that our space is between -1 and 1. In other words, when we actually made that Cherno logo in the textures video as an example, we plotted that geometry, like the vertex positions that we actually used there had to be between -1 and 1, and I think I wrote something like -0.5 to +0.5 or something like that, because without a projection matrix, we have nothing to we don't have an actual matrix to convert our vertex positions into that normalized device kind of coordinate space. So we have to provide it initially, because if we don't, if we're going to be well outside of that coordinate space, then we're not going to see anything on the screen, because as far as the screen is concerned, as far as what actually gets rendered onto our window, That has to be between -1 and 1. It has to be. But it's a bit difficult for us to deal with something that's just constantly -1 to 1. I mean, as an example, let's just say we're rendering a square, but our window is not square. It's 4x3 or it's 16x9. We can't just, I mean, we could theoretically do all the maths every time we calculate vertex positions and I guess keep doing the maths every time so that we do get a square. But wouldn't it be easier to just kind of be able to say, okay, well, how about the left side of our screen maybe is 0, the right side of our screen is width, so maybe my window is 1280 by 720. So let's just say that the left side is 0, right side is 1280, and I can render anywhere in between there, and then we'll worry about the maths of actually converting that into -1 to 1 later. So that is essentially what a projection can do for you. It lets you decide what your coordinate space is so that you can render objects however you like, whether they be inside the space, maybe they are outside of the screen because we're dealing with some kind of camera system that only shows the scene partially. A projection lets us do all of that. And for 3D, it's especially important because if you think about what a 3D scene looks like, it's not just as simple as kind of converting your projection from -1 to 1 and scaling it rather from a large kind of value into -1 to 1. So as that example that I just gave, from 0 to 1280 is my kind of projection matrix. I'm scaling that down into something that is -1 to 1. Might seem to you like, oh, that's easy, you know, I'll just divide this by like 1280 and like multiply it by 2 or whatever, subtract 1, you know, easy, right? Done. But if you think about a perspective projection, which is what is typically used in a 3D world, if you just take a photo of something and you take a look at objects that are further away actually become smaller. They'd be smaller in the photograph, right? And you don't even have to take a photo for this. You can just look with your own eyes and you can see, that, you know, that, you know, mountain over there is really just this big from here because of the way that perspective works. Because objects that are further away tend to look smaller. That is also an actual projection that needs to be applied if you're dealing with a 3D scene. And that's what a projection matrix can do. It will essentially look at the Z value and say, okay, well, objects with a larger Z value, if you use a coordinate system where positive Z is like far, those objects or those vertices with a higher Z value will actually end up being closer to the middle of the camera, which essentially will just make them smaller. So that's really important as well. And when we get into 3D stuff, you'll see how important a perspective projection is. But anyway, if we just take a look at this little PowerPoint slide that I prepared here, we have two different main types of projection here. We have orthographic projection and perspective projection. So orthographic projection is usually used for 2D rendering. Now, when I say usually, keep in mind, first of all,
we did orthographic here, bro.
Okay, here's a video of what fire looks like in zero gravity.
whilst orthographic is usually used for 2D, it's not always used for 2D. It's totally fine to use orthographic for 3D. That's actually done quite commonly because it presents a slightly different view that might be useful for something like a level editor or a 3D modeling program. Perspective's usually used for 3D, but I mean, everything is 3D anyway because there is the concept of Z. So if you're thinking of a 2D platformer, that might actually be using a perspective projection because there might be elements further away. If you look at a game such as Rayman, like the new Rayman games, they have that concept of depth, even though you can really only move on what is mostly kind of a 2D plane, a 2D axis. So don't take these as like, okay, perspective 3D, orthographic 2D. Not true. It can be used in both cases, but usually when we think of an orthographic projection, we think of rendering something like UI or something, maybe a 2D game or something like that. Whereas when we think of perspective, we think of like a first-person shooter or something like that where we actually have a 3D world that we're rendering. But that's not necessarily...
Let me search something up really quick.
Okay.
all they're used for. Anyway, what we see over here with this orthographic projection is that objects that are further away are not actually, they don't get smaller like they do with perspective. You can see these cubes, they look like they're further away because they're smaller, and our eyes are used to that because that's how we see in the real world. Whereas these two cubes here, they're the same distance. I mean, for all intents and purposes, what you see in these two diagrams that I just literally made in 5 seconds in PowerPoint using the shapes thing. Anyway, they're awful, I know. These things that are further away, they have the same vertex positions as these ones here. It's just that these are using orthographic projection and these are using perspective projection. Because, you know, these cubes do have the same width, the same height, the same depth, all of that, right? They just happen to be at a further Z value. And the perspective projection maths that actually goes on when we multiply these vertices with our projection matrix, that is what makes them smaller because they have a higher Z value. But at the end of the day, every single vertex position of all of these cubes gets mapped into a space that is between -1 and 1, and that is what the normalized device coordinates are. They're a space that are between kind of -1 and 1. Anything that is outside of that, so for example, if I have a vertex that ends up being calculated to be -2, that does not get rendered. It gets culled because it's outside of our actual view. It's outside of our frustum. Now, we're definitely going to talk more about, you know, these projections as we start to use them, but let's take a look at them in our code base. If I go back to my OpenGL code, over here, I have this projection matrix that I'm creating. So what I'm doing here is I'm saying I have an orthographic projection between -2 and 2 in X and -1.5 and +1.5 in Y. And then this is just the Z, the near and far. So we're not going to worry too much about that for now. Anything that I render, any vertex position, these are my vertex positions, any vertex position that lies outside of these bounds will not appear because this is the leftmost X bound. This is the rightmost X bound. So if I was to adjust any of these X coordinates to be, say, -2.5 or +5 or +100, they're not actually going to render because that is my view. That is all that I see. And at the end of the day, this orthographic projection, when multiplied with these vertex positions, is going to convert them to be in that -1 to 1 space. So as an example, since we have chosen -2 to 2, that means that 0 is in fact the center, the middle of our actual screen. If I have a vertex at -0.5, you can tell that that's kind of from the middle, it's a quarter of the way towards the leftmost bound because 0.5 is a quarter of 2. So since this orthographic matrix is going to convert this position to be between -1 and 1, then what is a quarter between 0 and -1? It's 0.25. So we can just tell just by eyeballing this, because this projection matrix is so simple, that this will become 0.25 on our actual screen. And if we do hit F5, it'll be a little bit hard to tell because I believe we are actually rendering a texture which is like partially transparent. In fact, yeah, I'm just going to get rid of that. If I go to my shader, I'm just going to make it so that we output, instead of outputting the texture color, we're just going to output white. So just vec41. And if we look at this now, you can see that if you kind of eyeball this, you know, this is the center of the screen here. And this leftmost kind of edge that we have from our square is a quarter of the way to the left because it becomes 0.25 where this, or -0.25, where this is -1. Hopefully this maths is kind of making sense to you. I don't really want to dive in and start drawing diagrams or anything because it's not really that useful to know this in practice. You just have to know that what the projection matrix does is it converts it into that normalized kind of device coordinate space of -1 to 1. That's really all that's happening. It's just a simple maths operation. There's nothing too fancy about projection matrices. If we go over here, and what I'm actually going to do is, in my application, I'm going to, instead of drawing this at 640 by 480, I'm going to convert this to be 960 by 540. And what I'm going to do now, well, let's
see, let's do that too. 960 by 540.
Just hit F5 and see what happens. Remember, we still have the same projection matrix. So it still kind of looks...
I'm rendering a dirt block right now, but... Okay, it does look different. It was a little bigger before. Interesting.
The same. I mean, it looks stretched out because we've changed the resolution of our window but kept the projection matrix the same. It's no longer, our square is no longer a square, it's kind of a rectangle. If we go back to our orthographic projection, let's play a little bit around with this. So what I'm going to do is what I mentioned earlier in my example, which is just changing it to be basically in pixel space, so a 1-to-1 pixel mapping. So to do that, I'm going to make 0 my leftmost edge, 960 my rightmost edge, because that's the horizontal resolution. I'm then going to make 0 my bottom and 540 my top. And I guess I will have to make this a float because this is a bit sad. Okay, cool. So let's hit F5. All right, cool. So we don't see anything at all. And that would be because, well, I mean, we do. It's just hard to see because, of course, if we are in pixel space, then this square is 1 by 1 pixel, which is obviously 1 pixel, which is tiny. So what we can do is just boost this. So I might just set this to be like 10.5 instead of 0.5. I'll just add a 1 here just to keep it simple still. And if we hit F5, you can now kind of begin to see it, but it's over here in the bottom.
That's uniform. Kuma, what are you making with OpenGL? I'm not currently making anything right now. I'm just learning. But I do plan to, after I'm done with this series, I plan to create a 2D, some 2D game. I don't know. I haven't really thought about it yet. And then hopefully kind of move to something 3D. Maybe, depends on how comfortable I feel at the end of this. Maybe I might look at some camera videos or something and try and build, you know, something in 3D. I don't exactly know yet. I'm just interested in graphics programming. So, you know, I started off at, you know, OpenGL.com, read a little bit, and then I kind of wanted something more visual, so I kind of started with Chono's series here. I mean, he taught me C++, so I'm kind of going from there, kind of doing a little bit of graphics programming. So that's the goal. I have no idea yet. Probably, I have an interest in recreating Minecraft, and I'm probably going to keep doing that on stream. I just have to get the foundation right on OpenGL, so that's currently what I'm doing right now.
Left, because what we've done, of course, is we've made the bottom, like our 0,0 coordinate to be the bottom left of our window. So if we scroll back up, what I'm going to do is just rewrite this. I was just going to modify it, but let's just rewrite it. Let's make this 100 by, well, we'll start at 100 by 100. And then I think we go anti-clockwise. It kind of looks like we are going clockwise. Give me a second here. Okay, cool. So we'll just say 100 by 100. Then we go anti-clockwise to the right. So we'll say 200 by still 100. And I'll just get rid of these 0.5s. And then we'll say 200 again for X. And 100 here, and then this will become 200, 200. Okay, so if we hit F5 now, with these new coordinates that we have here, we should see a square somewhere, and yes, we do. And if I go back to my shader, and I change this to be our actual texture, then you can see we get this rendering here. So what we've done here is you can see that really we've just played with the coordinate system a little bit. We've changed our projection matrix to be between 0 and 960 for X, 0 and 540 for Y. So essentially we've changed it to be per pixel based on the resolution of our window. And then because of that, we've had to adjust the positions of our geometry to actually be in that space. So rather than be like negative 0.5, positive 0.5, we've actually had to change them to be something a bit bigger, like 100 and 200 and all of that, because now we've redefined what space we actually define our vertex positions in. But at the end of the day, what happens is these vertex positions get multiplied with our matrix, and that is what converts them back into being negative 0.5 by 0.5. Let's take a look at another example. So just to make this absolutely clear, we have this 100 by 100. What I'm going to do is I'll keep my projection matrix, but I'll make a GLM vec4 and I'll call this VP, vertex position. and I'll just create a vec4 here that has the coordinate 100 by 100 and then 0, 1. Okay, so we don't have a z coordinate, and for w we're just going to specify 1. What I'm going to do then is type in glm vec4 result equals proj times vp. So I'm actually doing that multiplication myself right here on the CPU just to see what the result is, so that we can actually see. Now remember what I said. What we're doing here is this projection matrix is supposed to take our coordinate, our vertex position, and convert it into a space that is between -1 and 1. So if I hit F5 and I take a look at this, if we look at our actual projection matrix, it looks a bit wild. I mean, it's like 0.002, whatever. We don't really need to look at that. Our vertex position is, of course, 100, 100, 0.
Yo, you got the texture stuff to work? Yeah, I did. Yeah. I just had a few fixes. There was something actually really simple on my shader. I don't exactly remember what it was. It was a few days ago, but yeah, I got it to work. Yeah. So currently, whoops.
Are we ready for this party?
Currently rendering a dirt block that is flashing colors, like a disco dirt block, I guess. Currently learning a little bit about projection matrices. Kind of makes sense, but you know, I feel like, you know, the project work is where you really learn. I feel like I'm just getting introduced to this stuff, you know, in a way.
Guests are on their way, and food and drinks were just delivered.
Now, what about the music? It's got to be Manu.
My name is
learn by doing sort of person. So nice, yeah, appreciate it. Yeah, thank you. So I don't know, dude. It's definitely a grind, but I don't even know where I was at, dude.
Square is a quarter of, or -0. Start drawing diagrams or anything, because it's not really that useful to know this in practice. You just have to know that what the projection matrix does is it converts it into that normalized kind of device coordinate space of -1 to 1. That's really all that's happening. It's just a simple maths operation. There's nothing too fancy about projection matrices. If we go over here, and what I'm actually going to do is, in my application, 960 by same projection matrix, the projection matrix rectangle. If what I'm going to do is what I mentioned earlier, 60 0 my will have full and 1 test only
Look to this part.
2.5 bigger, like 1 say 0.5 by 0.5. What I'm going to do is that means 100 and change and take a look at the 79 and -0.62. If we look at this and we take a look at the bottom leftmost coordinate, that kind of makes sense, doesn't it? Like this, if we were to change our mapping to not use a projection matrix anymore, and we had -1 to 1, you could kind of imagine this as being around 70% of the way to there from the middle, right? So what it's done, clearly, is it has converted our 100 by 100 to be in that -1 to 1 space. And that is what projection does in both 2D and 3D. So in other words, orthographic or perspective. Again, nothing to do with 2D or 3D, it's just what people commonly associate them with. So in perspective and orthographic projection, doesn't the bottom leftmost coordinate, that kind of makes sense, doesn't it? Like this, if we were to change our mapping to not use a projection matrix anymore, and we had -1 to 1, you could kind of imagine this as being around 70% of the way to there from the middle, right? So what it's done, clearly, is it has converted our 100 by 100 to be in that -1 to 1 space. And that is what projection does in both 2D and 3D. So in other words, orthographic or perspective. Again, nothing to do with 2D or 3D, it's just what people commonly associate them with. So in perspective and orthographic projection, it doesn't matter, the same thing happens. All you're doing is you're telling your computer how to convert from whatever space you're currently dealing with, which is something that you define yourself, to that -1 to 1 normalized device coordinate space. And that is all there is to projection in OpenGL. Cool. Anyway, I hope you guys enjoyed this video.
Appreciate
if
it,
you
dude.
did, you can hit the...
I got the dirt block on the screen finally, dude. It's fucking flashing, dude. Disco dirt block. Guess that's what we'll call it. But yeah, you know, it's starting to come together a little bit, but it's definitely just like a little shaky, I guess, around some areas. But
like button, you can also help support the series.
You need that project work, you know, need to do a project and kind of learn from that. I feel like, at least for me, I say this all the time on stream, but I learn by doing. So let's take a look.
Hey, what's up, guys? My name is Achano. Welcome.
So model view projection. Isn't that kind of what we talked about? Projection matrices. That's model view projection. That's how 3D corners are projected onto a 2D screen. Yeah, okay, we learned that. While model view refers to a combined matrix that transforms an object local space into a common world or view space. The view model projection MVP is a series of matrices used to transform a vertex from its local or model space all the way to the final 2D position on the screen. Let's take a look at this Reddit. It's not linear transformation issue. I understand that linear transformations and matrices, and since we are working in 3D space, that means we cannot, for example, represent translation as just a matrix multiplication. If only space, and in 4D space, we can represent all rotation, translation, scaling 3D vertices, and multiplication matrices. Oops, that's
Back to my OpenGL series. So, last time we talked about projection matrices, and we basically, over the last few episodes, have gotten a math library into our application here that we're...
Got a text from my girlfriend, dude. I gotta respond. I've been too busy watching this. Okay.
Building in OpenGL. So today what I want to talk about is, I guess, the next step after the projection matrix. So we have projection matrices, and specifically we implemented like an orthographic projection for our view if we just launch our program from last time so that we can see what we actually had. We managed to draw this Cherno logo kind of in a different position, not in the center, and at the correct aspect ratio by using an orthographic projection.
I guess we should probably copy down that code. I guess he didn't really use this.
Which we provided over here in this line of code. So that's kind of one phase of it, the projection matrix, but there's also two other matrices that are fairly important when we're dealing with the transformation of geometry when we render it in a scene. So the first being projection, but then we also have something called a view matrix, and we have something called a model matrix as well. And all of that gets multiplied together with each vertex position to give us kind of the final position of the vertex in our actual screen, like inside our window, or in our kind of 2D projection that is on our computer screen. So again, lots of theory behind this, which I probably will cover at some point, but what I want to do today is just kind of introduce the concept and actually show you guys how you can access it and what it's used for. And then you can kind of play around with that and hopefully learn it that way, because that's probably a better way of learning it than just studying a lot of theory and not doing anything. Okay, so let's get straight into it. Model view projection, MVP, or in the other, if you reverse it, PVM, I guess, but usually it's set as MVP, and you may have heard that term as well, MVP, or MVP matrix. So that stands for Model View Projection Matrix. And that is kind of the transformation pipeline that goes through every vertex. Now I keep saying pipeline, but really what I mean is that each one of those letters, MVP, is a separate 4x4 matrix. And all of those matrices get multiplied together in that order model view projection. Now in OpenGL, since we deal with column major ordering, it's actually done in kind of reverse-ish. Like if we were to write it out inside our shader code or inside our GLM code in C++ here, it would be projection times view times model. Whereas like in DirectX, in Direct3D, because they deal with row major ordering for matrices, it would actually be MVP, model view projection. You'd actually have your vertex positions on the left side of that kind of equation. Not on the left side of the equation, but that would be kind of the first thing you multiply if you read left to right. Whereas in OpenGL, it's reverse. So the fact that it's MVP doesn't necessarily define the order. Lots of stuff we could talk about here that we probably don't need to mention. But the idea is that we have these three matrices and they kind of define different things for our vertex positions, because what happens in the end is we multiplied all the matrices together and we multiplied that matrix, that resulting matrix, with our vertex position. And that vertex position is the vertex position of our geometry, which is stored inside our vertex buffer. And that kind of, all of that multiplication transforms that vertex into where it should be on our actual screen, on our computer screen. That's what this is all for. So we have the projection matrix, which we talked about last time, which was specifically for actually converting this kind of whatever space we choose to work with into normalized device coordinates, meaning we're converting from whatever space we're dealing with, and whether that be orthographic or perspective, into a -1-to-1 mapping in kind of every axis, in X, Y, and Z. That's what the projection matrix is responsible for. Definitely check out that video if you haven't already. The model and the view matrix are something a little bit different. The view matrix, sometimes called the eye matrix, is kind of the view of the camera. So it's a way for us to kind of simulate a camera, more or less. And then the model matrix is a way for us to basically simulate the model.
Man, so many different things that they're talking about here, so many different matrices, just makes it like so fucking confusing. Like, it's like model matrix, this matrix, other matrix. It's like, bro, like everything's a matrix, you know, like.
Matrix. So the model being the model that we're actually drawing, so the vertex that we're drawing, and the matrix specifically is just a transformation of the model. So to put this into more simple terms, projection aside, because that just kind of defines, like, I guess, what kind of space we deal with, the view matrix is the position, the rotation, scale, whatever, of our camera. And then the model matrix is the position, there's the transform, so the position, rotation, scale of our actual model that we're drawing of our object. So we have the object transform and we have the camera's transform. Now, it's important to understand that at the end of the day, these are just mathematical numbers. The fact that I've kind of given you this illustration of we have a camera, we have this model kind of transformation matrix, that's all kind of an illusion in the sense that you don't have to have a camera. You could just, I don't know, you could just have your camera in the center at all times and just have the kind of model matrix, and that will work as well, because really these are just numbers and they all get multiplied together anyway. You could have another matrix that's like your secondary camera matrix or whatever. There's so many ways you could do this because it doesn't really matter. You're multiplying matrices together. You have to understand that. It's as simple as that. So the convention that we kind of deal with is we have a view matrix that is specifically supposed to represent our camera's kind of position and orientation. And then we have a model matrix, which is supposed to represent our object's transform, object being the thing that we're currently drawing. Because what will happen is we're going to multiply the projection matrix with the camera matrix, with the model matrix, with the vertex position. And we'll take a look at that in a minute. But conceptually, I just want you to understand that what I'm introducing here are two different matrices, the view matrix and the model matrix. The view matrix is supposedly supposed to represent our camera position and orientation, and the model matrix is supposed to represent our object's transform. Meaning, by transform, and I probably will make a video specifically on this as well. Teaching OpenGL is hard, man, okay? I'm gonna make a video on that as well, but transform specifically means kind of position, rotation, scale, or translation, I should say. That's the word I was looking for. It's been a long day, man. translation, rotation, scale, TRS. Translation meaning the kind of the position, I guess, of our object. The rotation being what orientation is kind of rotated in, and then the scale being kind of how big or small it is. It doesn't have to be uniform scaling either, so you might be able to change, like if it's a cube, you could make it like a rectangular prism or something like that. And we'll definitely get into that in the future as well. But that is the idea. Anyway, I'm gonna stop talking because I feel like I'm just gonna ramble on for another 18 hours. Let's just get into this and see what we can do with this newfound knowledge. So at the moment, what we have is kind of our base vertex positions, which are over here. We've created a projection matrix that is an orthographic matrix that is kind of from 0 to 960 and from 0 to 540. So in other words, it's kind of a pixel space projection here because every unit is 1 pixel. Here are our vertex positions, and those are just inside our vertex buffer. And what we're doing here, well, this result was just kind of me simulating that multiplication on the CPU side. But if you look at what our shader is doing, it's also doing that in the sense that it's taking our MVP, our model view projection matrix that we're passing in here, and multiplying it with position. Now, if we take a look at what MVP actually is here, you can see that what we actually pass in here is just this proj, right? We're just passing in that projection matrix. We don't have any kind of view matrix or model matrix. But what we're going to do now is we're going to add a view matrix. And what this is going to be is the position of our camera. So at this point, we need to decide, well, how do we want to move our camera? Maybe we want to translate our camera. We won't worry about rotation, just to keep this simple for now. Let's maybe move our camera, I don't know, 100 units to the left. Now, here's the trick. What we're doing here is we're trying to move our camera. So let's kind of, for a brief minute, because I will have a separate video on cameras, for a brief minute, let's just think about what a camera is. Well, okay, there's not actually, like, a camera doesn't actually exist. There's no such thing as a camera. So how would we simulate a camera? Well, let's just say we have an object like this phone over here, right? We have a camera here. So if I want to move the camera to the left, then the object would move to the right, technically speaking. So if I can't move the camera to the left, then the object kind of moves to the right. That's what happens. You probably can't see much on the thing. I probably should have just drawn a diagram. But that's kind of what I'm getting at. If you, like, there's no such thing as a camera in OpenGL. All we can really do, really, is just move geometry around. We can move vertices around. So to simulate a camera moving left, what we really need to do is move everything to the right. So it's kind of the reverse operation here. So what I'm going to do here is create a translation matrix, except since I want to move everything to the right 100 units, what I'm actually going to write here is a vec3 where I'm just moving everything negative 100, so to the left, because that will kind of be like moving the camera to the right. And I'll just fill in 0 for the other units here. And let's see what else this wants. So I guess what we should really probably do here is actually just create an identity view matrix, which would mean one of these, and then translate that matrix by just doing that. And I believe that should change it. Now, it takes in a const, which is great. So we'll actually have to, what we could do, I guess, is probably end up constructing a identity matrix here, and then assigning it to view like that. All right, cool.
GLM map4 view is equal to GLM translate. Oh. Is equal to GLM translate. What do we pass in here? A const GLM 844 GLM map4 0f GLM back 3 negative 100 0 0.
So that's kind of our view matrix. So now what we'll do is this MVP thing will actually create a GLM map for MVP matrix, which will be that projection times the view now. So let's pass that into MVP here and hit F5 to run our program. All right, cool. And
view projection. And then we pass in our MVP. I don't know. I don't exactly know what this is going to look like on the screen, but I guess we'll see. Okay. I mean, it looks fine. Can't really tell any difference, but he's got different.
So the result here is that this channel logo has just moved 100 units to the left, because what we've done is we've moved our camera to the right, and if we move our camera to the right, it means that everything else in our scene kind of moved to the left. And I've simulated that by just doing the reverse operation here, because I'm typing in -100 here, which essentially ends up moving the object to the left, which again is a simulation of moving the camera to the right. So that's how that works. Obviously, if you write a camera class, you'll this kind of negation, you'll automate all that, and the API will take care of that for you, so you don't have to worry about that. But mathematically, that's how it works. Moving the camera to the left is actually just moving all the objects to the right. So with this same principle, because all we've really done here, I mean, you can't tell the difference. I've called it view matrix, but you can't tell the difference between us moving the camera to the left or us moving the object to the right. Same thing. So it's, again, purely a kind of way to visualize how this actually works, but mathematically it's all the same, it's just numbers. So what we'll do now is we'll create this model matrix, and I'll again translate
model matrix.
the model somewhere. So we ended up translating this, well, the camera, we ended up moving to the right. So what I'll do here maybe is move the model up a bit. So maybe we'll move it 200 to the right and 200 up. And so we should basically end up
200, 200, 0. Yeah.
with our channel logo being closer to the center of the screen. And we'll multiply all these matrices together. So projection times
projection view times model.
View times model. Hit F5, and you can see now we have the channel.
I don't think mine's moving very much because mine's a little different to his. He's doing his in pixels. I'm doing mine differently. Yeah, I'm still doing my... I don't really know how to explain it, but my space between 0 and 1. Oh, sorry, -2. I have to relook at this. -2, 2. Let's see here. Let's grab this code here. Widely mismatched coordinate scales. Okay, so I'm doing mine. Okay, yeah, so that's why I'm doing mine in pixels. Times bigger than any type visible. This means your model disappears immediately. I was supposed to use G-line mat 3 MVP, but MVP should be mat 4. Should this be mat 4?
Channel logo projection time.
Oh, whoops. Okay, let's do small translations here. So for -1.0 F and like 2.0 F, 2.0 F. Oh, no, we see nothing. Okay. Let's get rid of this. Get rid of the model for now. Let's see. Okay, so that works. So we move it to the left here. But if we want our model times by model, we have to go. Let's do like let's do like 1.0 F, 1.0 F. Okay, I think that moves it up. Moves it right again and moves it up. Because it was down here, so we moved 1.0 this way, 1.0 up. Yeah, because I think our distance here is 1.5 from the top and the bottom. So I think that makes sense. I gotta piss really quick. I'll be back in a second. Be 2 seconds. Okay, I'm back.
Times view times model, hit F5, and you can see now we have the channel logo being moved another, 200 units up and 200 units to the right, okay? And that's what we end up with. Cool. So this resulting matrix here is what our MVP is, model view projection. And again, the multiplication is kind of in reverse order. That's to do with the memory layout of all the numbers, the fact that they're in column major. You can kind of think of reading matrix multiplication in OpenGL as right to left. So we multiply model with view with projection. That's just how it ends up working out because of the way that we've laid out our memory, because of the way that OpenGL actually expects it in the shader, in the GPU, and also the way the GLM handles it for us because of that kind of specification by OpenGL. But anyway, that's what you see here. 3 matrices multiplied together, which create the transformation for our actual vertices. That's it. Very simple. Camera multiplied with the transform of our object, multiplied with that projection, which converts everything into normalized device coordinates. That is basically all the matrix multiplication you need to know if you're worried about positioning objects in a 3D or 2D world. That's it. That's all there is to know. Obviously, you can do more than just translation. I kind of just showed you a simple example. Now, what I want to do next time, because we've kind of touched on all this kind of model view projection stuff in this episode, which is awesome. Next time, I want to actually start introducing perspective projection and maybe get into some 3D stuff. Now, because it's going to be really important for us to have some kind of way of controlling these parameters live, because I can't keep closing my application, changing the code, recompiling it, and updating it, that's going to be really painful, and it's really hard for me to demonstrate anything like that. What I'm actually going to do is probably integrate IMGUI, which is a kind of a UI framework. Really easy to use UI kind of layer that we can use for actually kind of having UI controls as part of our application, which we can use to modify variables while our application is running. It's kind of like a debug layer. Really easy kind of UI to use. So we'll probably integrate that next time. But other than that, we're just going to progress, keep going with this kind of math stuff, and hopefully get into perspective projections soon and think about how we can render real world kind of objects on the screen, whether that be 3D or 2D. We might go back and forth between 3D and 2D, I haven't decided yet. But that is kind of the gist of this. Let me know what you guys thought of this whole model view projection thing. I am going to probably end up making more detailed videos about each concept, but I kind of like to make an overall video just introducing the topic first, because this is probably enough information for a lot of you to actually start doing this yourself and play around with it. And that's going to be probably the best way to learn. Anyway, I hope you guys enjoyed this video. If you did, you can hit that like button. You can go ahead and help support this series by going to patreon.com. Hey, what's up, guys?
Alright, cool. So we learned about model view projection matrices, how to manipulate that with the camera movement, so that was interesting. Obviously, I need to practice it a little bit more. I think what I'm going to do here is I'm going to end the stream here. I'm going to go make some dinner, because I'm fucking pretty hungry, not going to lie. And I'm going to get back to it tonight. I think my girlfriend's coming, I think, tonight. I don't know for sure. If she does come, I probably won't stream tomorrow. But if she if she doesn't come, then I'll probably will stream tomorrow. So it just depends. Depends how long she stays for. So that'll probably be my streaming thing for this weekend. But hopefully, you know, I'll be able to get through this. Hopefully, you know, by Thanksgiving, so then we can start kind of building something more interesting on stream. But yeah, appreciate you guys watching. Sorry, I'm not feeling the best today. I'm honestly pretty sick. I have been having body aches all day, so it's been pretty tough. But appreciate you guys watching. Peace. You guys should follow me on GitHub if you haven't already. Maybe look better than what I am. Appreciate all the love. Thank you guys for the help. And